Hi guys, we're gonna start on a new chapter, which is really just an extension of Newton's laws. So we're still gonna use all of the information that we learned from chapter 5, like writing the sum of the forces in the y, writing the sum of the forces in the x, and then determining what's accelerating. We'll still see things maybe with an Atwood's machine, we still may see things on inclines, but now I want to incorporate what we learned from chapter 4 about circular motion, and I also want to incorporate Newton's laws with that. So how would I ask you a Newton's law question if we were talking about circular motion? So just a little bit of review from chapter 4. We have uniform circular motion, which remember is when it's moving at a constant speed. So the only type of we do have an acceleration, and that acceleration is centripetal acceleration. Remember, we can find centripetal acceleration because a sub c, which we represent as centripetal acceleration, is equal to v squared over r. So that's just how I would find centripetal. So if it's uniform circular motion, remember we're not going to have that total acceleration vector. So we don't have radial, we don't have tangential, we just have centripetal, which centripetal means center seeking. So there's a few different types of problems, I think, are major categories of problems that they can ask us. So for uniform circular motion, we just said there's a centripetal, it's based on a centripetal force, which is based on a centripetal acceleration. Centripetal acceleration is always directed inward toward the center of the circle. Centripetal, thus meaning center seeking. So if I want to find centripetal force, it's going to be force equals, or the sum of the forces equals mass times centripetal acceleration. So we've seen this before, m times v squared over r. Okay. It acts toward the center. We already know that. Let's say, for example, that this puck, or whatever this object is moving in circular, uniform circular motion. If this string breaks, we know that that puck is just going to move tangent to that circle, right? So it's just going to continue to move in that linear path that it would have moved in if it weren't for that center-seeking force. Okay, so if the force vanishes, the object would move in a straight line path tangent to the circle. So let's talk about, in this video, two different types of problems that I could ask you involving forces and circular motion. The first type is called the conical pendulum. Conical pendulum. So this says, and this would be a great FRQ question. It says a small ball of mass m is suspended from a string of length L. The ball revolves with a constant speed v. So I know we're talking about uniform circular motion because of constant speed. And it revolves in a horizontal circle, and that has radius r. So if I'm looking here, I have my mass connected to some type of rope, some string that's hanging maybe from a ceiling, and then that's just going to go around in a circular type of path. My goal is to find an expression for speed in terms of the geometry, okay? So how would I do this? I want to set this up just like it is one of our force problems. We're going to do a sum of the forces in the y, and think about the sum of the forces in the x, and then our goal is going to be to try to set this up for v. So let's do this. Just like I gave you the situation, I want you to draw a free body diagram, and I'll draw this picture too on the Promethean board. Okay, so our picture looked like, just kidding. I don't like green. That's a terrible string. I'm sorry. Okay, so here is the length of my string. That's L. Tension will also be directed up the length of this string. So tension is also there. It's going to move in some type of circular path. Okay, so radius is going to be directed. That's a terrible radius. Oh my gosh. Radius is going to be directed along the radius. And theta was made here. So that was a theta. Okay? Let's draw a free body. I want to draw a free body for that particular mass. If we draw the free body, I know that I have tension acting on it, and then also that mass is going to have a weight force. So my free body diagram would have weight force straight down, and then the tension is at an angle. And I'm just going to direct it, I'm going to do it this way. So if theta is here, I finished my triangle on the opposite side, so theta would be here. Okay, so there's theta. These are the only two forces that are acting on it, so this would be my free body. Let's set up the sum of the forces in the y. Let's set up the sum of the forces in the x. So the sum of the forces in the y would be t cosine theta minus mg. And since it's only moving in the circle in the horizontal direction, I can say that it wouldn't be accelerating then in the y, so that's going to be equal to 0. So if I simplify that down just a little bit, t cosine theta equals mg. I want to do the same thing, so I'm going to just call this equation number 1, okay? I want to do the same thing, but I want to do that for the sum of the forces in the x. In the x direction, I only have one force that's causing that acceleration, and that would be t sine theta. And that equals mass times the acceleration. But the acceleration in uniform circular motion is centripetal acceleration. And we already know a formula for centripetal acceleration, and that is v squared over r. So I want to plug that in. So really this should read t sine theta equals m times v squared over r. Okay? So this is my second equation. I want to utilize these two equations, and my goal is to utilize them in such a way that I can try to cancel out as much as possible to just be left with v. Okay, that's my goal. So to do that, I'm going to end up taking and dividing one by another. And I'm doing this because I want to try to eliminate as much as possible and try to simplify this down as much as I can. So if I did sine theta over cosine theta, that'd be tan theta. So right now, I want to take equation 2 and divide it by equation 1. And let's see what happens if we do that. So I would have t sine theta equals mv squared over r. And I'm going to divide that by t cosine theta equals m times g. To simplify that, I'm going to take that r and just go ahead and put it under here, okay? Because that's the same thing. Let's see what happens. Tension cancels. Sine theta over cosine theta now becomes tan theta. So now I have tan theta here. That equals, masses are now gone, they cancel. So then I'm left with v squared over gr. So this is a much simpler way that I can try to solve for the speed, because that's my goal, let's solve for speed. So all we're doing right now is trying to derive that expression for v. If I rearrange this, just for v, I would end up getting v is equal to the square root of tan theta times g times r. Okay, but I could simplify it even more so, because my goal is to simplify it in terms of its geometry. And I can try to simplify maybe this r. So, and I know this is a simplified version already, but I want to take it just one step further. Okay, in this triangle, I can think about them as forces, but then I can also think about, here's L, this would be then my radius, and then theta was up there. So I want to write r in terms of the geometry of the length of that rope. And I could do that by saying that r equals L sine theta. So let me plug L sine theta in for r here. So V equals the square root of tan theta g L sine theta. That's my answer. Okay. So all we did, we utilized the fact of a free body diagram, and I wrote some of the forces in the y, some of the forces in the x. I know I set something equal to each other here on 1 and 2, so I just said this is going to be equation 1, this is going to be equation 2. My goal is to use these equations to simplify down as much as I can, and I did that. I did that by dividing the two, because then I get tension to cancel out, I get masses to cancel out. The reason that I'm doing that too is because I want you to see that speed has nothing to do at all with the mass of whatever it is that's moving in that horizontal circle. So it is independent of mass. So hopefully we're kind of just seeing that a lot of these things are independent of mass, because we saw some examples of that in chapter 5. But it is dependent, or can be dependent, on the length of the string, okay? And it definitely depends on theta. So conical pendulum definitely depends on theta, and it can absolutely depend on the length of the string. Okay,